Okay, good day. So let's have another example for the design and analysis of a bolted connection. But this time we have eccentrical loading and we are to use elastic analysis method. Okay, for this example, determine the most stress bolt or bolts and the required diameter of bolts to be used in the connection using elastic analysis method. So this is our connection. So first thing to do is we need to locate the center of gravity of all bolts. So we have the center to center distance of all bolts horizontal is 75 mm and vertical center to center distance of all bolts is also 75 millimeters. So therefore, we may not use Barignons. It is obvious that the center of gravity of all bolts will be along the line of this second row of bolts. So this is the location of the center of gravity of the bolt. So basically midway of 75 mm. So we can now compute for the eccentricities. So we have the eccentricity along x-axis, that is for the 200 kilonewtons load. Eccentricity along x is equal to, that is half of 75 plus 150. So these units are in millimeters. So we have that as 100. This is 187.5 mm. Then for the eccentricity along the y-axis, this is for the 300 kilonewton load. So that is basically 60 plus 75. So let's say this is our E sub y is equal to 135 mm. Okay, so since we are using elastic analysis method, we also assume that our loadings, the 200 and the 300 kilonewtons, are also acting on the center of gravity of the bolts. So therefore, we assume that the reactions of the bolts will be equal, or these loadings will be distributed to the bolts evenly. So for the 200 kilonewtons load, since that is a vertical load, let us compute for the direct shear. So let's say this is the direct shear for 1 bolt vertical, that is a P sub dy. So computing for the direct shear, so for the direct shear, we assume that the loadings will be distributed evenly to our bolts. So we have, we can do it first. For the vertical force, summation of forces vertical equal to 0. So again, class, we have 6 bolts. So that is 6 times the vertical direct shear for 1 bolt is equal to 200 kilonewtons. So what will be the direct shear? What will be the direct shear for 1 bolt? Considering the vertical load, 200 kilonewtons, that is basically 200 divided by 6. So what is 200 over 6? That is 200 divided by 6 is equal to, let's say this is 33.33 kilo newtons. So 33.33 kilonewtons per bolt. Then what about the direct shear for the horizontal loading? So we have a horizontal load of 300 kilonewtons again, since we are using elastic analysis. So we assume that the horizontal load 300 kilonewtons is also acting on this center of gravity. Therefore, we assume that the reaction per bolt will be equal. So let's say this is the direct shear. The direct shear per bolt along the with respect to the x-axis, or with respect to this horizontal load 300 kilonewtons. So again, we have 6 bolts. So this time we can do summation of forces horizontal equal to 0. So we have 6 bolts. The direct shear for 1 bolt P sub dx is equal to 300 kilonewtons. The direct shear along x is now equal to 300 divided by 6. Okay, this is obviously equal to 50 kilonewtons. So 50 kilonewtons per volt. So since again we have eccentrical loadings, there will be a torsional effect on our connection. So let us compute for the net torque acting on this connection. Okay, so when it comes to the torque, so again from our strength of materials, so torque is basically a twisting moment. So let us compute for the moments with respect to the center of gravity. Okay, so what are the moments with respect to the center of gravity of all bolts? Okay, so first we have the 200 kilonewtons. Let's say that will be our moment number 1. So 200 millimeters, 200 kilonewtons, I should say, multiplied by the eccentricity is 187.5 mm, or we say that is in meter, 0.18, 75 meter. So that this moment will be in kilonewton meter. So what will be that value? This is 200 multiplied by 0.18, 0.1875. So we have that as 37.5 kilonewton meter. So with respect to the center of gravity, obviously this moment is a clockwise moment. Then our moment number 2, that will be from the 300 kilonewton meter. So this is 300 kilonewtons multiplied by the eccentricity E sub y 135 mm or 0.135 meter. And this moment is equal to 300 multiplied by 0.135 is equal to 40.5 kilonewton meter. And if you are to observe, its direction with respect to the center of gravity of the bolts, so obviously that moment is a counterclockwise. Okay, so this moment is counterclockwise. So therefore, if you are to compute for the net torque, that is basically equal to the summation of the moments. So considering that, again, clockwise moments will be positive. So this is equal to, what is our clockwise moment? That is 37.5 kilonewton meter. Since m sub 2 is counterclockwise, this is negative, minus 40.5 kilonewton meter. So we have a net torque is equal to, so I think this is negative 3 kilonewton meter. Again, it is negative, which means our net torque is a counterclockwise moment, or a counterclockwise torsion. So let's have, so from this torque, let us compute the shear, or the torsional shear force caused by this torque. So since we have now the torque or the torsion, so we can now compute for the torsional shear. So for the torsional shear, how do you compute for the torsional shear per bolt? We have the torsional shear, let's say with respect to the, or that is caused by the horizontal load, P sub Tx is equal to the total torque, or that is the net torque, divided by the summation of this squared multiplied by the value of y. So how do we compute for the this squared? Let us first check the coordinate of all bolts with respect to our center of gravity. So we may assume that our center of gravity will be our, in terms of the coordinate system, the rectangular coordinate system, let us just assume that our center of gravity, or the center of gravity of all bolts, will be at the origin. So for the bolts, so let's say this is bolts, we have 6 bolts, so this is 1, 2, Okay, 3, 4, 5, and 6. So we have the bolts ay 1, 2, 3, 4, 5, and 6. So what will be their abscissa, or that is the x, and the ordinate, or that is the y. For bolt number 1, its coordinate is half of 75 is 37.5. It will be at negative 37.5. Then bolt number 2, it is on the right, so it will be positive 37.5. Bolt number 3, again, that is also negative 37.5. Bolt number 4, the same, that is positive. That is on the right of the center of gravity. So this is positive 37.5, and 5 is negative 37.5. And the last one, this is 6. That is at positive 37.5. So basically, rectangular coordinates. Okay, when it comes to y, so obviously since 3 and 4 are along the center of gravity, so their y value will be 0. So 0 and 0. Then again, so we have 1 and 2. They are on the same position above the center of gravity. That will be positive 75. And we have bolts 5 and 6 are in the same position, or the same row below the center of gravity. So since below, that is negative 75. So what is that d, the d distance? So basically, the d distance is the distance from the center of gravity of the bolts to the center of the bolts. So this is the d distance. So from our problem, we are required to compute for the most stress bolts. Okay, so when it comes to eccentrical loading, so the most stress bolts are sometimes called as the critical bolts. Okay, so critical bolts are basically the farthest bolts from the center of gravity. Okay, so take note that the critical bolts, or the most stress bolts, are the farthest bolts from the center of gravity. So basically, what will be our concern? So we may conclude, okay, for this example, okay, so we may conclude that our critical bolts are bolt number 1, bolt number 2, bolt number 5, and bolt number 6. Okay, so how do we compute for the direct shear with that caused by the 300 kilonewton load? That is the horizontal load. So therefore, we may just focus to these bolts. Bolt number 1, number 2, number 5, and number 6. So how do we compute for the value of d? So the value of d, or the summation of d squared, is basically the summation of the x squared plus, this is the summation of y squared. So let us compute. So as you can see, we have 637.5. All of them are 37.5. So it doesn't matter if it is negative or positive, since the value will be squared. So positive or negative, that will give us a positive value, since again, they are squared. So let us compute. Okay, we have the summation of the d squared is equal to, so take note, we have 6. Okay, we have 6 horizontal distance from the center of gravity, that is 37.5. So again, it doesn't matter if it is positive or negative, since it will be squared. Okay, then plus how many? 75. So again, we have 75, 75, negative 75, and negative 75. It doesn't matter if it is positive or negative, since it is to be squared. We have 4. So that is 4 times ay 75 squared. So this will be the equivalent of the summation of this squared is now equal to, okay, we have 6 of 37.5 squared, okay, plus 4 times 75 squared. So let's have it as 30,937.5. So 30,930, okay, 37.5 okay, millimeters squared. Okay, so we can now compute, okay, for the direct shear caused by this horizontal loading, okay, the 300 kilonewton load. So this time, we are computing for the shear caused by torsion per bolt. So let's say this is piece of T of X. So again, our concern bolts are bolts number 1, number 2, number 5, and number 6. They are equidistant, okay, from the center of gravity, and they are the farthest bolts. So therefore, they are the most stress bolts or the critical bolts. Okay, computing for, what about, what is the value of their Y? So the value of Y from the center of gravity is basically equal to 75 mm. Okay, computing for this value, you have the piece of Tx is equal to, what is our total torque? Our total torque is 3 kilonewton meter. But just to be uniform when it comes to our units, this is the same as negative 3,000. So multiplying 1,000, so that the unit will be 3,000 kilonewtons. Okay, kilonewton meter. Kilonewton millimeters. I just converted this meter into mm. So multiplying 1,000. So again, the negative sign indicates that our net torque is counter-clockwise. So our net torque is equal to 3,000 kilonewton meter. Okay, the distance of the centroid of the bolts 1, 2, 5, and 6 from the center of gravity is basically equal to 75 mm. That will be the value of our Y. So multiplied by Y, okay, the value of Y is 75 millimeters. So this is in terms of mm. So 75 mm, okay, divided by the summation of the D squared, we have that as 30,937.5 square mm. So this will be the direct shear or the shear per bolt due to torsion. So we have the torsional shear along X is now equal to, so this is equal to 3,000 kilonewton mm multiplied by 75 divided by 30,937.5. This is equal to, let's say, 7.27 kilo newtons. So that will be the torsional shear along X. So what will be the torsional shear along Y? So for the torsional shear along Y, that will be the torsional shear piece of Ty is equal to the net torque divided by the summation of the D multiplied by X. So what is the distance of the centroid of each bolt to the center of gravity of all bolts horizontally? So obviously, that will be our X. So the value of X is equal to 37.5 mm. So again, 37.5 mm for all critical bolts 1, 2, 5, and 6. So computing for this value, we have piece of Ty is now equal to, the total torque is 3,000 kilonewton mm multiplied by the value of X is 37.5 millimeters to be divided by the value of the summation of the D squared, which is 30,937.5 square mm. So computing for the value of the piece of Ty, okay, this is 30,000, 3,000 multiplied by 37.5, then to be divided by 30,937.5. So in kilonewtons, this is 3.64 kilonewtons. So these are now the torsional shears. So based on the direction of the loading, the torsional shear with respect to the x-axis will be to the right. That will be the reaction of the bolt. And the torsional shear with respect to the vertical loading, that will be upward. So P sub Ty. So again, our focus are just the critical bolts, bolts 1, 2, 5, and 6. Okay, so by the way, so these are per bolt. So torsional shear per bolt. And a little correction here, it should be summation up this grade. Okay, so now we have the values of the direct shear. So you have the value of the direct shear and the torsional shear. So let us focus on one of the critical bolts. So let's say that is critical bolt number 1. So for bolt number 1, so what will be the direction of the reactions or the direct shear? So since our loading is downward, so obviously our direct shear reaction will be upward. This is the direct shear for our critical bolt number 1. A piece of dy upward. Then when it comes to the direct shear horizontal, since our loading is horizontal, 300 kilonewtons, obviously the reaction of the bolt will be to the right. Let's say this is our P sub dx. Okay, now when it comes to the torsional shear, so the same. Our torsional shear along the x-axis is P sub tx, that should be to the right. And our torsional shear with respect to the y-axis or along the y-axis, it should be also upward. So this is P sub Ty. So we are now computing for the resultant reaction of 1 bolt. This is the P sub, let's say P sub 1. Okay, that will be the reaction, the total shear acting on our critical bolt, bolt number 1. So basically, that will be the resultant of these 4 elements. We have our P sub 1 is equal to the square root of. So along x, that is the direct shear along x. Okay, that is the P sub dx, plus the torsional shear along x, the P sub tx. Okay, quantity squared, plus. Okay, when it comes to the direct shear along y, we have P sub dy plus the torsional shear along y, P sub ty squared. Okay, so all we have to do now is substitute to compute for the total shear acting on 1 bolt. Okay, we have this is P1 is now equal to, this is the square root of, what is our P sub dx a while ago? So P sub dx a while ago, that is the 50 kilonewtons per bolt. And P sub dy is 33.33. So those are the direct shear. So we have P sub dx is 50. Okay, that is 50 kilonewtons per bolt. Okay, plus our P sub tx per bolt is equal to 7.27 kilonewtons. So 50 plus the 7.27 kilonewtons, quantity squared, plus direct shear along y, that is the 33 kilonewtons, plus the torsional shear along y is equal to 3.64 kilonewtons. So this is 3.64 kilonewtons, quantity squared. So the resultant shear acting per 1 bolt is equal to Okay, we have the square root of 50 plus the 7.27 squared. Okay, plus 33.33. Okay, plus 3.64, the quantity squared. So we have that as 60, or a little correction here. So I was not able to put 7.27. Okay, that is equal to 68.16. So this is, okay, we have 68.16 kilo newtons. So now if you are to compute for the required diameter, let's say we are to use a 325 volts. For a 325 volts, so the value of the shear capacity F sub NB is equal to 457 megapascals. So anyway, this value is on our NSCP 2015. Okay, so we have basically the value of P, or that is the shear capacity, is equal to F sub NB multiplied by the area of the bolt. So per bolt, the actual shear of our critical bolt is equal to 68.18 kilonewtons. So let's say this is 68.16 kilonewtons. So multiplying 1,000 to be in newtons. So the shear capacity for A325 volts is equal to 457 megapascals. This is 457 newtons per square mm. And the area of 1 bolt, let's say that is pi times the diameter of 1 bolt. Let's say the base of b squared divided by 4. So what will be the required diameter of 1 bolt? 68.166, so multiplied by 1,000 to be in kilonewtons. This value to be divided by 457 megapascals. Then times 4 divided by pi. Then we take the square root. So let's say that is equal to 13.78 mm. So this value is close to 14 millimeters. But for a designer, for us to increase the factor of safety, if we don't have, I think we don't have 14 mm, or maybe there are 14 mm diameter bolts, but just to increase the factor of safety, we can say, or we can use, maybe it is more ideal to use 16 millimeter diameter bolts for this design. Okay, so just to increase, or just to be sure, just to increase our factor of safety, I will be using 16 mm. So this will be our solution for this example. So the most stressed bolts are the farthest bolts from the center of gravity of the bolts, of all bolts. And using elastic analysis method, the recommended diameter of bolt will be, I will be using 16 mm A325 diameter, 16 mm diameter bolts which are A325 bolts.